Is my screen visible to all of you?
Yes, sir.
Okay. And I'm audible, right? Okay. So welcome to week 5 discussion of this course, Introduction to Machine Learning, and this course was originally taken by Professor Balaraman Ravindran, Professor and Head of the Department of Data Science and Artificial Intelligence, IIT Madras, and myself, Ayan Paul. I am a PMRF research scholar from IIT Kharagpur, and I am a TA of this course. TA means I am a PMRF TA of this course. My duties are I will interact with you all. I will discuss some of the questions that are very much related to your assignment, so that when you will solve assignment, you will not feel alienated. That is my duty. But before that, what I will do, I will just make you understand some concept that will be very helpful regarding solving your assignments. Okay. So welcome to week 5 discussion. Okay. So last week, what we have discussed, about perceptron and support vector machines, right? Now this week we will be learning about neural network. Okay. So neural network, artificial neural network. Okay. Neural network. When we talk about neural network, generally we are talking about the neurons that is in our brain. Okay, that is the neural network, original neural network. So this artificial neural network is a model inspired by structure and function of biological neural network in human brains or animal brain. Okay, so that is artificial neural network. So neural network, what it consists? It consists of lot many of neurons that are connected to each other. Okay, so here this is a picture of biological neuron. Okay, this is the picture of biological neuron. Now biological neuron, you can see some of the parts, these are dendrites. Okay, now this is known as nucleus. Then this is the cell body in which the nucleus and dendrites are in, and then the information passed to the branch like structure called axon. Okay, and then there are outputs, and then again a neuron will be connected like that. Okay, so this is a structure of a biological neuron. Okay, now our artificial neural network, it also contain neuron, that is known as artificial neuron. Okay, so an ANN consists of connected units or nodes. Okay, these are connected unit or nodes. Generally if there are two neurons, we have to if there is a neural network means there are threads or layers. Okay, now to connect those threads and layer, there should be a node at the end point as well as at the starting point. So this nodes is known as neurons, which loosely model the neurons in the brains. Okay, so if I draw an analogy with our artificial neural network, this is a biological neural network and below is the artificial neural network. Okay, so if I draw an analogy similar to our biological neuron, our biological neuron also receive information. Okay, it receives information, this x1, x2, x3, x4, these are all inputs. Okay, or information that is passed on to this dendrites. Okay, now this now this all the information goes to a nucleus. Okay, and after it goes to a nucleus, the nucleus process the information and transfer it to the branch like structure called axon, and then this information will be again shared by next neuron. Okay, so this inputs in our biological neuron system is known as synapse. Okay, synapse or message. Similarly in artificial neural network, these are known as inputs only. Okay, now the inputs, it goes it it comes through various dendrites. Okay, these are dendrites. So in dendrites in case of biological neuron, but in artificial neural network, the inputs, it goes to a neuron through some kind of weights. Okay, w1, w2, w3. Okay, now now every input has some weight. X1 will be having some weight to this neuron. Similarly, the next input x2 will also have some kind of weight to the neuron. Similarly, x3 and xn all have some kind of weights. Okay, so these are weights. Now after the information reaches to this nucleus, it will do two functions: summation as well as activation. So how it will sum it up? Like w1 x1 plus w2 x2 plus w3 x3 plus w4 x4 plus wn xn. So that is summation function. Okay, this is the summation function. So after that summation function, we have a threshold unit, or it can be called as some kind of activation unit. Okay, so activation unit, after this the information is summed up, the information will be going through a function. Okay, so that function is known as activation function. So after that activation function, the whole information is processed and it will go to the next neuron. So that is how our neural network function. Our neurons function in both biological system as well as artificial system. So at the top diagram, this is about biological system, and at the bottom diagram, this is about artificial neural network system. Okay, so functioning, each artificial neuron receives signals from connected neuron then processes them and send the signal to the other connected neuron. Okay, the signal is a real number in case of our artificial neural network. Okay, in case of biological neurons, this signal is known as synapse. Okay, and the output of each neuron is computed by some function of some of its input called the activation function. So I have already told you, first the information with some kind of weight will come into the nucleus. It will first add up, that is we will sum it up, like w1 x1, w2 x2, x2 w3 x3 and so on. Okay, so we will sum it up. After summing it up, it goes to an activation function. So after that activation function, your information will be fully processed. The strength of the signal at each connection is determined by weight, which adjusts during the learning process. So how a neural network learns, that is the most important question, right? So what happens is this weights get updated time by time. In the previous okay, let me shift it. In the previous lecture, what I have told you, how a perceptron determines its output or classify the correct output. What it does, it updates the weight. Similarly, in case of neural network also, what it does, it reaches the reaches the lowest error by updating its weight. Okay, so that is how the neural network function. Okay, so any doubt in this slide? Any doubt in this slide? Okay, okay, okay. So let me move to the next slide. Okay, so I have told you, first the information will get sum up, and then the information will go to through some function. Okay, so that function is known as activation function. So what are the different activation function? You need to learn them. So first type of function is known as step function. Step function, what it will do, all the negative inputs, it will if the your input is negative or less than 0, the output will be 0. Okay, if your input is greater than or equal to 0, then your output will be plus 1. Okay, so that is step function. So its range 0 and 1, only 0 and 1. Okay, it is used in hidden layer, output layer for classification. Okay, about layer I will be discussing in the next slide. Until now you just remember that there is a step function. Step function, what it will do, if your input will be negative, it will return 0. If your input is greater than equal to 0, it will return 1. So that is first type of function, activation function. This now is the second type of activation function. uh, Second type of activation function is the signum, or also known as sine function. Okay, so it is very similar to your step function, only the case is if your input is uh, less than 0, then it will return -1. If your input is greater than equal to 0, then it will return +1. Okay, there will be equal to also. Okay, greater than equal to 0, then it will return +1. So its range is -1 and +1. Now the third type of function is known as linear function. Linear function, it will return the output as the input. Okay, whatever will be your input, it will return the same output. Okay, so that is linear function. That is fz equals to z, means any input you will supply, same will be your output. Okay, so that is linear function. Its range is between -infinity to +infinity. Now the fourth type of function, it is a very important function, that is rectified linear unit, ReLU function. Okay, this is very much used. Rectified linear unit. So what this rectified linear unit tells is, if your input is less than 0, it will return 0. If your input is greater than 0, then it will return that input only. That is, if your z is less than 0, it will return 0. If your z is greater than equal to 0, it will return z. Okay, so that is rectified linear unit. Its range is between 0 to infinity, plus infinity. Okay, minus terms, all it will minus terms, if it will take, it will return 0. So that is why your range is between 0 to plus infinity. Now, okay, someone is joining. Okay, so yeah, so this is your rectified linear unit, or ReLU function. Your fourth function is leaky rectified linear unit. Okay, leaky ReLU. Leaky ReLU is very much similar to your ReLU function, only what it will does, earlier if your input is less than 0, it returns 0, but here if your input is less than 0. Okay. So if your if your input is less than 0, it will return az. Okay, a is any small positive number. Okay, if your input is greater than equal to 0, it will return z only. Okay, so that is leaky relu. Now our fifth is hyperbolic tangent, denoted by tan hz. Okay, what it will return? It will return e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z. Okay, so that is hyperbolic tangent. Now range is between -1 to +1, and this is the graph. Okay, sixth is the sigmoid function. This is your sigmoid function. Now e to the power z by 1 plus e to the power z, that is the sigmoid function. We have also learned about sigmoid function in the earlier classes also, when we are doing your classification thing. So same thing, logistic regression. So same thing is your sigmoid function. Sigmoid function, it will fz will be e to the power z divided by 1 plus e to the power z. Okay, or we can write it as 1 by 1 plus e to the power minus of z. Okay, its range is between 0 to 1. Okay, it will not go to negative side. Its range is between 0 to 1. Now there's a last activation function known as softmax activation function. It is very much similar to your sigmoid function only. Only difference is yeah, only difference is here for each neuron, we will for each neuron in the output layer, it is basically used for output layer neuron only. So each neuron of the output layer, we will be calculating our fz value. So fz for first neuron in the output layer will be equal to e to the power z1 divided by e to the power z1 plus z2 dot 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 zn. Similarly, e to the power ith layer will be e to the power zi divided by e to the power z1 z2 plus dot 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 zn. Okay, so this is softmax function. Okay, so that is all about activation function. Now yeah, I will be coming to that, but let's discuss this also, and then I will be taking your doubts. Okay, so neural network architecture. So up to this, we have been talking about neuron, and we have been talking about activation function. But now, what about the structure of the neural network? So that we will see. So typically neurons are aggregated into layers. Okay, layers. Different layers may perform different transformation on their input. So the feature of layer is that each layer will have a single transformation function. Okay, so that is the feature of a layer. Now signals travel from first layer, the input layer, to the last layer, output layer, possibly passing through multiple intermediate hidden layers. So how many layers are there? There will be input layer, there will be output layer, and in between all the layers, that layers are known as hidden layers. So that many layers will you will get in a neural network. Okay, a network is typically called a deep network if it has at least two hidden layers. Now if it has at least two hidden layers, then your neural network will be called as deep neural network. Okay, now here there are some types of neural network. So this is the single layer feed forward neural network. Okay, so feed forward, what does feed forward means? Feed forward means your information will only travel in positive direction or forward direction. So that is feed forward network. Okay, now single layer feed forward network means your neural network will only have one layer only. Okay, like here you can see we have only one layer of neurons. Okay, so that is why this neural network is known as single layer feed forward neural network. Now we have the most common type of neural network called multi-layer feed forward neural network, in which you have an input layer, you have an output layer, and in between all the layers are known as hidden layers. Okay, that is multi-layer feed forward neural network. We have a third type of neural network, recurrent neural network architecture. Now what this recurrent neural network means, your information can go in positive direction as well as negative direction also. That means your information can travel in forward direction as well as backward direction also. Like here in all this two architecture, you have seen your information is only going in forward direction. Here the arrow is in the forward direction only. Similarly here also you will focus and see your arrow is in the forward direction only, but here the arrow is also in the backward direction only, means the arrow is in forward as well as the backward direction. So that is why this type of neural network is known as recurrent neural network, not feed forward, it is recurrent, means the information coming out of the neuron will can go back in the backward direction also. So that is why this type of neural network is known as recurrent neural network architecture. Now going to the previous slide, here it has been written which layer, which activation function you have to use for which layer. So generally this step function, signum function, etc. is not used for a hidden layer. Okay, it is been written here, but actually this step function, signum function, all type of threshold function. What is threshold function? Threshold function means your value will be 0 1 1 minus 1, etc etc. So all this type of, okay, people are joining. Yeah, so all this type of yeah, all this type of threshold function will not be used generally in the hidden layer. We use this step function or signum function or any kind of threshold function in the output layer only. Okay, now a linear function can be used in a hidden layer as well as output layer, but it is used for regression purpose only. Okay, now this step function as well as this signum function or threshold function, these are basically used for your classification problem only. Why classification? Because it has got two output, 1 and minus 1, or 0 1 or 1 minus 1, whatever. So that is why we generally use this for classification problem. Now here ReLU function can be used for hidden layer as well as output layer for regression. Okay, now this leaky ReLU we use for a hidden layer as well as this can also be used for output layer also, according to me. Now hyperbolic tangent, hidden layer as well as output layer for classification. Now it is not a threshold function, still this hyperbolics and sigmoid function, this is used in output layer for classification, because its value is between minus 1 to 1 or 0 to 1. That means we can have a threshold, like let's say 0 is your threshold. Below 0 we can term it as one class, above 0 we can term it as another class. So we generally use this hyperbolic tangent or sigmoid tangent. For sigmoid tangent also we can have a threshold like 0.5. So below 0.5 we will be termed it as class 1, above 0.5 we can term it in class second. So that is why this type of hyperbolic function as well as sigmoid function can be used for output can be used in output layer for classification. Also it can be used in the hidden layers. And last, softmax function is designed specially for multi-class classification. Earlier the classification I was telling, these are binomial classification or binary classification, means only two classes, but this softmax classification is used for multi-class classification and it is used in the output layer. Okay, so any doubt? Any doubt in these two slides? Very important slides, activation function as well as neural network architecture. So any doubt in this? Yeah, Anand, please.
Sir, are these the only functions, or are these functions enough to model the neural network, sir, or there are some more?
No, there can be some more, but these are the popular and the most used cases. Okay.
Okay.
And this ReLU function, this is a very important function. This is even used for modern neural networks also. Okay. This softmax
Okay.
function is also a very important function that is used for classification. Hyperbolic, sigmoid are always used. So these are very popular type of activation function and mostly used. Okay.
Thank you. Thank you.
Okay. Okay. Any doubt? Any doubt regarding this two slide? Anyone else? Any doubt?
So some GLU is also there, right?
Yeah, can be there. I have not included.
Okay.
Okay. You can learn about different type of activation function. Okay.
Leaky relu, what's the advantage?
Leaky relu, see, earlier in relu, what we were doing, if the input is negative, we are reducing it to 0. That means the output will be 0 only. But leaky relu, when the input is also negative, it will return some kind of output, and that output will be alpha z or a z. Okay, so we are not neglecting the information. Okay, if you will get 0 with the activation function, that means in that from that neuron you are completely wiping out the information, right? Because your output is getting 0. But in leaky relu your output will be az. That means a into the input. A is some kind of positive, small positive number. So that is the advantage. Okay. 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 Yeah,
Sir?
Anandari. Yeah.
Sorry, sir. Sir,
Okay.
we are modeling the neuron activity only. No? So, this is a very silly question. Do we know that this is the right? This is how the neuron really functions, or we are just modeling it
Means
based
biological. Yeah, yeah.
using mathematics?
Biological neuron. We are.
Biologically.
Yeah, yeah, yeah. We know this. Okay.
Oh, okay,
From
okay.
that we have modeled our artificial neuron from biological neuron only. Okay.
Oh, okay, sir. Thank you, sir.
Okay. So we will move on to the next slide. Okay. Which is very important. So how the learning in this multi-layer feed-forward neural network happens. Okay. So we will be considering this example and we will see how the learning will happen. Okay. So here this is a neural network architecture. Okay. Okay. Okay, so here you have layers. Okay, so I have told you in multi-layer feed-forward neural network you will have input layer, you will have many hidden layers, and then you will have output layer. Okay, so input layer is denoted by I, hidden layer is denoted by H, output layer is denoted by O. Okay, and I11, that means yeah, I11 means we have one layer of input, that is why I11 that is the thing. Okay, I11 you can also say it I1. Okay, so first neuron, as we have only one layer of input, so I1. Okay, I1 I1 I1M means whatever the neuron, this is the first neuron, that is why I I11. Okay, I similarly this is the ith neuron I1I, this is the mth neuron I1M. Okay, so that is the nomenclature. So this is regarding input. Okay, I this is I1 I M. Okay, I means on the input side, IO means on the output side. Okay, so again I am repeating. So I1, this is the nomenclature I1. Okay, that means we are talking about information in the input side. In the input layer also there will be two sides, right? Input side as well as output side. So I1 means I1 means your input one on the input side. IO1 means your IO1. Okay, IO1 means your input on the outside on the output side of the first layer. So IO1. Okay, in between there will be some kind of activation function in between. Okay, so that is why I1 IO1. Okay, so that is the nomenclature. Now there will be weights to connect to the hidden layer. So these weights are denoted by V. Okay, so this will be V11, this will be V12, this will be V13, V14, V15, etc. Now we have hidden layer. Hidden layer, again you have input side, you have output side. So HI1, HO1. Okay, Now we have weights. Now we have weights connecting your hidden layer to the output layer. So that is denoted by W. So that will be W11, W12, W13, etc., etc. Okay. Now after that, your information reaches your output. Your output will also have two sides: input side of output and output side of output. Okay. So O I1, O O1. Okay. So this is the entire thing. This is the input layer consisting of m neurons, and we are giving it as a transfer function, linear transformation function. Hidden layer, we have n neurons. Okay, in the hidden layer we are giving it as it giving a log sigmoid transformation function. This is just an example. Okay, and then output layer we have p neurons. Okay, and we are giving it as tan sigmoid transformation function. So is it clear up to this? Is the nomenclature clear to all of you? Shall I again tell?
Sir, yes.
Clear, right? Okay, nice. Now now the thing is how our neural network learns. The neural network learns by updating the weights. Okay, this V and W, these are the two weights, right? So our neural network can learn if it can update this V and W. Okay, so that is how our neural network learns. So this is an error curve. If I plot your weight with respect to the error that is coming, what is the error? Error is the target output minus the predicted output. Okay, this O1, OOK, OOP, these are predicted output, but there will be a target output. So the target output minus your predicted output, that will be your error. And always in neural network or anything, what we do is we are interested in finding square error. So square error will be T over O1 target, if I denoted your target by T. Okay, so TO1 minus your OO1 OO1 and square. Okay, so that is your error. Okay, up to this it is clear, right? Target minus the predicted square, that is the error. Now your error is
What is this V?
hello, any questions?
This V and W. What
You are
is
not
this V
audible.
and W?
Hello,
Yeah. What is this V and W?
what is this?
V and W. V.
V.
Yeah, V and W.
V and W. V and W are the weights. Okay. V is the weight connecting your neurons from the input layer to the hidden layer. Okay, that is V. The weights connecting your hidden layer to the output layer is W. Okay. So this is V and this is W.
It
Is
will
it
be a
clear?
number, is it? It is a
Yeah.
probability.
Yeah. It will be number. We will be doing one example. In that example, it will all get clear. Okay.
Okay.
Okay. Now this is an error plot. Okay, if we are plotting our weights with respect to error, this is our error plot. Okay, now this is our 2 dimension. If we are taking it in 3 dimension, because we will have a different V and different W, this is the error surface. Okay, now there is a delta rule. What is the delta rule? Delta V, delta V will be equal to minus eta del E by del V. Delta W will be minus eta del E by del W. So why we are using delta, why we want delta V and delta W? Because we want to update the weight. And your updated weight will be equal to previous weight plus your delta V or delta W. Here we are talking about W, so that is why delta W. So that is your updated weight. Now this the delta W same minus eta del ek by del W jk. Okay, now the thing here is, the problem here is, if I want to calculate del E by del W, so here will be your error, right? Del E is TO1 minus TO1, means your error will be somewhere here, but you want to differentiate in terms of W. So in between there will be this term, and then you will reach here. So you have to apply chain rule. So your del ek by del wjk will be equal to del ek by del ook, because we are here. Okay, we are here, so we have to go here or here first. So del ek by del ook, okay, and then del ok by del ok with respect to del oik, del ok with respect to del oik, and then del oik with respect to your w. By this we will reach here. So again I am repeating, we are here tok. From tok we have to go here, from here we have to go here, and from here we have to reach here. So that is why we have applied this chain rule. Okay, so this is all about, yeah, del ek by del ook will be minus of tok minus ook, because when you will differentiate you will get this. Okay, and there is a minus sign because generally we are doing yeah, generally okay, yeah, there will be minus sign. Why will be why is there minus sign? Because when we are differentiating, this is negative, so that is why minus took minus ook. Okay, so that will be your del e by del ok. Similarly, if we will update this v weights, we are updating the w weights. Okay, now if we will update, now if we will update this v weights, we will having this same formula, del vij is equal to minus eta. Eta is your learning rate. Okay, minus eta del e by del vij, and then you will again apply the chain rule, because you are here. From here you have to go here, so that is why from here to here, here to here, here to here, and then here to here. That is why you are applying this chain rule. Okay, so del ek by del ok, del ok by del ik, okay, and then del oik del oik by del hoj, and del hoj by del hij, and del hij by del vij. Okay, so is this clear? You got something at least? Then we will be discussing the question, and the question it will be very much clear. But is something clear? Something you got from this slide? Anybody?
Yeah.
Any question? No question, right? Okay, so main thing is this. Okay, for learning our neural network, what we have to do, we have to update the weight. How we are updating the weight? We are updating the weight by adding a value of that weight. So how we are how this what is this value? This value will be minus eta. Minus eta, eta is your learning rate, del ek by del w jk. Similarly, if I tell what will be delta v, delta v will be minus eta del e by del vij, whatever the notation. Okay, so this is the thing. So is it clear? Any questions? Okay, so let's move on to the question. It will be very much clear. So this is a figure below, shows, yeah, it is talking about this figure, shows the schematic view of a neural network also called NN, or you can call it ANN, consisting of 3 layers. You can see 3 layers. This is the input layer, in between there is a hidden layer, and there is a output layer. The neuron lying on the input, hidden and output layer have transfer function or the transformation function, anything you can, or activation function, anything you tell. The transfer function represented by y equals to x. Okay, so in this layer your activation function will be equal to y equals to x. In this layer your activation function will be equal to y equals to 1 by 1 plus e to the power minus x, that is sigmoid function. In this layer you will have your activation function y equals to e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus of x. There are 2 inputs. In the input layer you have 2 inputs, namely I1 and I2, and 1 output. This is the in the output layer we are having 1 neuron only, that is why one output, that is why we are keeping 1 neuron only. The connecting weights between the input and the hidden layer are represented by V. Okay, this weights we are telling V, and this weights we are telling W. and those between hidden and output layer we are tailing as W. So this is V and this is W. The initial value of the weights are assumed to be, these are the initial value of weights, V11, V12 and V13. That means when your first neuron will be connected, first neuron of the input layer will be connected to first neuron of the hidden layer. So in that case we will be writing V11. Similarly, first neuron of input layer, second neuron of hidden layer, V12. Now first layer of input neuron and first neuron of input layer and third neuron of hidden layer we will be writing V13. So that is why 3 weights. Similarly with V2, V21, V22, V23, and these values are given here. Now you have similarly for the weights between your hidden layer and output layer, that is denoted by W. So W we have when the first first neuron of the hidden layer is connected to the first neuron of the output layer, we are calling it as W11. When the first neuron of input hidden layer is connected to second neuron of hidden layer is connected to first neuron of output layer, W21. Third neuron of hidden layer connected to first neuron of output layer, W31. That is why we have 3 weights, W11, W21, W31, 0.1, 0.2 and 0.1. Now here it is given a target value is also given. Okay, so the output that we will predict, that is the predicted output, that is not the real output. Our target output is given, that is 0.15. Our inputs are given, I1 is given 0.5 and I2 is given 0.4. Now here in the question, using an incremental mode of training for the case shown in the table, calculate the changes in V, del V and W, that is del W, values during back propagation of error. The learning rate eta is assumed to be 0.2. Okay, learning rate is assumed to be 0.2. Show only one iteration, means we have to do it for one iteration only, not second and third, or we have to only do it for one iteration only. So is the question clear to all of you? Very important, is the question clear to all of you?
The, we won't be discussing about the error on this, or we will be calculating this error while doing.
Can you tell a bit clear? Your voice is very
No,
unclear.
regarding error, we will be calculating in our solutions.
Regarding
Error, that is what we will be calculating in the solution.
not error, we will be updating the weights. Yeah, we will first calculate error and then we will be updating the weights.
Okay,
That we
okay,
have to do. We have to
okay,
calculate del V and del W so that we can
okay,
update the weights in one increment only. That means in one step only. Okay.
okay, okay.
Sir, weights and the given input V1 and W1 will be given, no, sir?
Yeah, V1 is all
Value.
V is already given, and also
Yes,
W is already given.
already they will given.
Yeah,
Just
yeah,
we have to calculate that W and this V.
yeah,
Okay.
exactly.
Okay, sir. Okay.
Okay, any more doubt? Okay, so let's go to the solution. Okay, now our input layer. Okay, this is the input layer. The input layer, what type of function we are using? We are using linear function. That means your I1 will be equal to I01. Okay, that means your transformation function has no rule. So I1 will be equal to I01. Okay, so that is only written. So I1 is given, that is 0.5, right? This is your I1. Okay, I1 is 0.5, I2 is minus 0.4. So I1 is given, I2 is also given as your transfer function or activation function is linear. So that is why y equals to x. So that is why your output that will be coming from this activation function will be I01 will be same as I1. Okay, so is this clear, this step? One by one step I will be talking, so please, if anyone will have any doubt in any step, kindly please let me know. Okay, so I think it is very much clear. You have two inputs, right? I1 and I2. So this is on the input side. So I1 and I2 you already have. Now what will be your IO1? IO1 will be determined by this function. Okay, and as this function is y equals to x, so IO1 will be equal to I1. So that is only written. Okay, now the inputs of different neurons of the hidden layer, how we will calculate the inputs of different layer of the hidden layer. So hidden layer also have two part, HI1, HO1. So first we will be calculating HI1. So how your HI1 will be calculated? HI1 will be calculated, see this neuron. Okay, this neuron is taking your input from this first neuron as well as this second neuron of the input layer. So this neuron will have your V11 into your IO1, uh, uh, then uh, then yeah, V11 into IO1 and V21 into IO2. Okay, so again I am repeating, it will be V11 into IO1 and V21 into IO2. Similar for HI2, HI3. So again I am repeating, see this neuron, focus on this neuron. This neuron will have contribution from first neuron as well as second neuron of the input layer. So HI1 into V11 and IO1 into V11 and IO2 into V11. Similarly, if we will talk about the second neuron, then it will have contribution from first as well as second. So it will have contribution from these two arrows. Okay, that is V12 into IO1 and V22 into IO2. Okay, so this is about HI2. Similarly, you can calculate HI3, that is IO1 into V13 plus IO2 into V23. So is this clear, this step? Any doubt regarding this step? Any doubt regarding this step? Second step, how your values on the input side of the hidden layer is calculated. See, just this, weight into your input. Okay, W1 into X1. This you have to remember. So W1 into X1, see weights over here. V11 into this the value on the output side of the input layer. So V11 into IO1 plus VO2 into IO2 into V21. Okay, so this neuron is over. Similarly, you can calculate about this neuron as well as this neuron, and we are talking about input side, not the output side. How the output side will be calculated? Output side will be calculated by this transfer function, because here again you have a transfer function. So by applying this transfer function, you will calculate HO1, HO2 and HO3. Okay, okay, and now we will be calculating our output side, output neuron. Okay, so output neuron also will have two sides, input side of the output neuron and output side of the output neuron. So first we will calculate input side of the output neuron. So that will be equal to HO1 into W11, because we are connected with only one weight. So HO1 into W11, HO2 into W21, HO3 into W31. So by that your OI1 will be calculated, and O1 will be calculated by putting this transfer function. Okay, so when you will apply this transfer function, you will be calculating O1. Okay, so this is your O1. Now this is your predicted output, but we have a target output. Your target output is 0.15, but you are getting 0.195692. So by this you will calculate the error. Here we are generally calculating half of the error, half of the squared error. Half of the squared error is calculating because when we differentiate this term with respect to the O1 or etc., what happens is you know the x square differentiation is 2x. Okay, so half into 2i's of that, so 2 and 2 will get cancelled out. That is why we calculate half of the squared error. So this is your half of the squared error. So up to this, any doubt? No doubt, right?
Why we are taking this half, please?
Yeah, half. See, you know the differentiation of x square, right? Differentiation of x square is 2x. Okay, so if we will differentiate half of x square, it will be half into 2x. That will be 2 and 2 will get cancelled out, so you will only be left out with x. That is the main purpose of taking the half. Okay. Okay, so any doubt regarding this, please tell, because this is the first step. How we got the output? Any doubt? Predicted output? How we get? Any doubt? No doubt, right? Okay, so let's say nobody has any doubt. Now the change in yeah. Now we have to our work is not over. We have to calculate delta W11, and that will be equal to minus of eta del E by del W11. Now again, what I have told you, see this. Now we are at this side. Okay, we are here, and we have to calculate our value with respect to W11. So before that, we have to first go from here to here, and then from here we have to go here. So that is why we have to apply the chain rule. Okay, so chain rule, del E by del W11 will be equal to del E by del O01 into del O1 by del OI1, and then del OI1 del OI1 with respect to del W11. So when you will solve this, you will get some value. Okay, so this is the value. Similarly, you have to do it for delta W21 and delta W31. Okay, so again I am repeating, we have to calculate delta W11. Similarly, delta W11. So how we will calculate delta W11? That will be equal to your error divided by del of W11. Okay, del E by with respect to del of W11 will be equal to del E by del O01 into del O01 by del OI1 into del OI1 with respect to del W11. Okay, so by this you will reach, because see this diagram. Okay, we are here, somewhere here, our error is here, and now we have to propagate our error to this W. So in between we have to go from error to output. Okay, error to output. Now error to output of the output layer, then output layer to output of the input side of the output layer, and then from input side of the output layer we can go to W11. So that is why we have to apply chain rule. Okay, so you have to you have to differentiate. So when you will differentiate del E by del O1, you will get this. When you will differentiate del OI by del OI1, you will get this, and when you will differentiate this with respect to del W11, you will get this. Okay, now when you will put all the values, you will get del E by del W11, and you have eta value, right? Eta value is already given, right? Eta value or the learning rate is given 0.2. So you have this 0.2 is given. Okay, so you have to find delta W11. You have eta value is given, that is 0.2, and you have just calculated this del E by del W11. So you will get delta W11. Similarly, you can calculate delta W21 and delta W31. So any doubt in this? In this slide, how we have updated the weight of W? No doubt, right? Okay. Now we will be doing the same with delta V11. Now delta V11, again you see this, we don't have direct link of E with respect to V, right? First we have to go from E to OO then OO to OI, then OI to this H, and then from H to HO to HI, and then HI to this V. Okay, so again we have to apply this chain rule. Okay, so after applying this chain rule, you will solve this, and you differentiation of del E by del O1 already we know. This also we know, and then this also we know, and then you have to find out del H O1 by del H I1 and del H I1 by del V11, and this two you have to find in this step, and then you have to put all the value eta, you all know that is 0.2, and then you will get del then you will get delta V11, that will be equal to minus of 0.2 into this value. So you will get this. So by that you can have change in your delta V11. Similarly, you can have change in your delta V21, delta V12, delta V22, delta V13, and delta V23. Okay, so after all these changes, now you will update the weights. So this is your updated value of weights. Earlier this is your value of weight: 0.2, 0.4, 0.3, 0.1, 0.6, 0.5. Now once we have calculated delta V11, so we have to just add it. That means earlier your weight was 0.2. Now we have to add this delta V11. This delta V11, that is plus of minus 0.000110. So your answer will be V11. You will get this. Similarly, you will get V12, V13, V21, V22, V23, and similarly you will get your updated weights for W also. Okay, so is this clear? This is the whole question. So is this clear? Any step, any doubt? Kindly tell me. This is how we updated the weight. So any step, any doubt? Right from your question to your solution. Any doubt? Kindly tell me, right? Yeah, Anand.
In real time, how many times will we do this iteration?
Hello.
Yeah. In, in real time, how many times we will do this iteration?
Until we reach the target output.
Okay.
Okay.
Sir, this is Anand.
Yeah, please.
Sir, what caused this change in values, weight, sir? Somewhere I missed something. What caused the change in the caused us to update the weights?
What update the weight?
And something should have changed, no? Something
Yeah,
should have changed
yeah.
for the weights to be updated. What changed,
Your weights are updated, right? This is
right?
your new weights: V11, V12, V13, V22, V21, V22, and V23. This is
What
your
initiated the updation, sir?
initially this was your weight, right? Initially this are your
Yes.
weights. Now we have updated the weights. Now what is your
You mean,
question?
so just going forward and backward
Information is
cause
only,
the weights to change.
yeah. We are
Oh,
changing our error with respect to weight. Okay, you see this. Your updated weight will be equal to your previous weight plus change in weight. Okay, now we have to calculate the change in weight because we have the previous weight. Now to get the updated weight, we have to only calculate this change in weight. So how we will calculate this change in weight? A change in weight will be calculated by minus eta. Eta is your learning rate into del E with respect to del W J K. Okay, because here we are updating weights of J K, that is why J K, and this del E K. E K is your error only. Okay, so this is your error with respect to this weight. So by that we have updated the weight, and once you will calculate this, you just put this over here and you will get your updated weight. Okay.
yes, sir. Yes, sir. Thank you, sir.
Okay, the only trick is we cannot directly calculate del EK by del WJK. Why we cannot calculate? Because you see this. Okay. You see this. Whenever we are calculating error, we are somewhere here, right? We are this is our target output, so we are here. But we have to go from from this T01 minus O1, let's say this is E. Okay, this is E. So E, okay, yeah, your E is somewhere here, but from here we have to go here, right? From E we have to go here, so we cannot directly go, so that is why we have to apply chain rule. From E we will go to O1, from O1 we will go to OI1, from OI1 we will get to this W. So this is the trick. Similarly, in case of V, we cannot go from E to V directly. We have to go from E to O1, then O1 to O1 to OI1, then OI1 we have to go to H. Okay, from H to HO1 to HI1, and from HI1 to V. So that is the only thing. So by that we will calculate our del E by del Vj as well as del E by del Wj. Okay, this is the only trick. Okay, any more doubt? Anyone, any doubt? Kindly ask me, please. Everyone got this, right? This is a very important question. This is the whole concept of back propagation in the neural network. Back propagation, why we are calling it as back propagation? Because errors are backwardly propagated, right? So that is why back propagation.
Actually, in our question, the target of the output has been given. This PO has been
Your voice is not clear. Kindly repeat.
in our question, we have got the targeted output, right? I mean to say the TO has been given in our question.
Can you write your question? Actually, it is very unclear, or someone else might help me because your voice is very unclear actually. Okay, we are having the targeted output. Yeah, target output already is given to your question. Now you have to now you have to find out predicted output. Okay, and from target output to predict output, then you have to go to update your weights. That is the trick. Should I again tell? Do we need to repeat the iteration? Yeah, you need to repeat your iteration until your predicted value will be very close to your target value. But here, as here in the question, as it is mentioned only one iteration, that is why we have solved for one iteration only. Okay, it has been mentioned in the question, right? You see this, it has been mentioned in the question, show only till one iteration. So that is why we have solved till one iteration only. Okay, which value should be equal to TO plus, please? TO target output is already given, right? 0.15. Your inputs are given and target output is given. Now you have to find out your predicted output. Okay, O1. And once you have target output and predicted output, you can get the error. Now what you have to do, you have to differentiate that error with respect to your this weight and this weight, so that you can get the change in weight. Once you get the change in weight, you have to update the weights. Is it clear? Can you please show me the OO? Okay, OI1 and OO1. Okay, this is the OO1. Yeah, there is nothing, it's just coming, it's nothing. Okay, this is nothing, because this is your activation function. Okay, this is your activation function of the output layer. Y equals to e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. So this is your transformation function. Okay, so this should be equal to 0.15, that is TO, right? This is your predicted. Okay, this is your predicted. Your actual or target output is 0.15. Yeah, this should be equal to 0.15, but as it is not equal to 0.15, so we need to update the weights again and again. Okay, but as in the question it has been asked for one iteration, that is why we have solved for one iteration only. Okay. Any more doubt in this question? This is a very important question. Kindly don't feel shy. Please ask if anyone any question, any part, any question. Okay. So let me move to the next topic. So your next topic is maximum likelihood estimation. Yeah, this is your next topic. So it is a method for estimating the parameters of the statistical model given a data set. Okay, your data set is given. Now you have to estimate the parameter so that you can maximize the likelihood of the data. That is why it has been called maximum likelihood estimation. So the goal of MLE, or the maximum likelihood estimation, is to find the parameter values that maximize the likelihood of the data given the model. This is done by choosing value of the parameter that make the observed data most probable. Okay, so we have to find the value of the parameter so that our probability of the distribution will be maximum. Okay, so that is the concept of your maximum likelihood estimation. Okay, so we have been only given data. Okay, from that data we have to calculate the maximum probability. So how the maximum probability can be calculated from that data? If we know the correct value of the parameters which will maximize the probability value. Okay, so that we have to find out. So this is the example. So this is the data. You can see here these are two sides of coin. Okay, this is, let's say this is tail and this is head. Okay, so your data will be from this space, subspace, that is head as well as tail. Okay, so whenever you will be tossing the coin, it will be head or tail. And in this data you have first one is your head, second one is your tail, head, head and tail. Okay, so now the probability of head, this is a parameter. Okay, now we have considered it as theta, and probability of tail will be 1 minus theta, because these are dependent parameters. Okay, now MLE chooses theta that maximize the probability of the observed data. So we have to find out theta which will maximize the probability of the observed data. So choose the value that maximize probability of the data, and theta that will give the maximum probability of the data, we call it MLE. That is maximum likelihood estimation. And how this MLE is calculated? That is argmax. Argmax is nothing but d with respect to divided by d theta. Okay, this we have to maximize it. That means we have to find out d by d theta, and then you have to equate it with 0, and that by that we can maximize that thing. That is why it has been told argmax theta. That means d by d theta we have to calculate. That means differentiate with respect to parameter, and then whenever we will equate it to 0, that will give either maxima or minimum. Okay, this case it will give maxima, so that will be your answer, or that will be the value of the theta. So this is the thing. So theta MLE, this same formula, p d theta. D is your data and theta is your parameter. Okay, so be given the data, you have to calculate the parameter. Okay, this d means first what will come first, that will be given. Okay, so p d theta means given the data, you have to estimate the parameter. So this will be can be written as this, because in this is a type of Bernoulli distribution. That is why it is written as this, that p xi theta. So when you will solve this, you will get this alpha theta alpha h and 1 minus theta alpha h. Alpha is nothing but the number of times. Okay, number of times the head, that is alpha h, number of times the tail, that is alpha t. So this will be your this whenever we are opening this you will get. Now we have to do the differentiation on j theta. Okay, so d j theta by d theta, when you will differentiate it, you will get this thing. So this thing will be maximum likelihood estimation. theta MLE, that will be equal to alpha h, that is number of time of h divided by number of time of head plus number of time of tail. Okay, so if you are given 5 flips, okay, and you got 3 head and 2 tails, so your theta MLE will come 3 by 5. Okay. Okay, so this is about maximum likelihood estimation. So again I am repeating, maximum likelihood estimation, it is a method for estimating the parameter of a statistical model given the data set. So you have been given data set, now you have to find the parameter. Okay, that is the thing. Now different type of function will have different parameter. In a Bernoulli distribution, your parameter, important parameter is your p. Okay, p or probability of that particular event. Okay, that is denoted here by theta. Okay, so our goal, the goal of MLE is to find the parameter value that maximize the likelihood of the data given the model. This is done by choosing the value of the parameter that make observed data most probable. So we have to find theta such that our probability will be maximum. Okay, p d theta will be maximum. We have to find the theta so that p d theta will be maximum. So that is our target. So how we will find out? We will first solve for p d theta, and it will be this, and then we will be differentiating this with respect to theta, and when differentiating this will be our answer. And okay, and here in this question or this example, here 3 heads are coming and 2 tails are coming. So if head is a success, so theta MLE will be equal to 3 by 5, because 3 heads and 2 tails, so 3 divided by 3 plus 2, that is 3 by 5 will be our answer. Okay, so is this clear? Okay, so let me move on to the next thing, that is maximum posterior. Okay, so earlier in maximum likelihood estimation, we have data and we have to know the parameter. Here we have data and also we have a prior information. Two things are given. Here with data set we have some prior knowledge about the model. Okay, now we have to calculate the same thing, that is parameter. But earlier we have only data. Now with data we have some prior knowledge about the model. So this is the difference between MLE and MAP. Again I am repeating, MLE we have only data and we have to find the parameter. Here with data we also have a prior knowledge about the model. So by that we have to find out the parameter that will maximize the probability. Posterior probability, that means the updated probability. Okay, prior probability means probability of the distribution. Now posterior probability means the updated probability. Okay, this is done by choosing the value of parameter that makes the data most probable given the prior knowledge. So this is the formula. Earlier you can see the formula p d theta. We have to we have to find out theta so that this p d theta can be maximum. Now we have to find out theta so that p theta d will be maximum. Okay, theta d is same thing, but here with data set we have a prior knowledge about the model. So this is the difference. Now this p theta d can be written as p d theta into p theta. This is by a theorem called Bayesian learning. So Bayesian learning, what it tells us that p theta with respect to d, p theta given d will be proportional to p d given theta into p of theta. That means it can be posterior probability can be written as multiplication of prior probability into this likelihood estimate. Okay, so this is the thing. So this we already have calculated from the previous question. If we have p theta, then we can find out the theta MAP. So this is the thing. Now there are some points about MAP. You see, MAP is similar to MLE. Where is the difference? But it incorporates prior knowledge about the model into estimation process. Again I am repeating, MLE we have only data, we have to calculate theta. so that our probability will be maximum. Here in MAP, besides data, we also have a prior knowledge about the model. Okay, so this is the only difference. Here also we have to calculate the parameter so that our probability will be maximum, but here we all have a prior knowledge. That is the difference. Now MLE and MAP are same when prior distribution is uniform. If this term is constant, okay, if this term is constant, then what will happen is whenever we will do this d by d theta, or whenever we will differentiate our term, if this is constant, then what will happen? This posterior probability and likelihood probability will be equal. Okay, so this is the thing. Your MLE and MAP will be same if your prior is uniform distribution. When your prior is uniform distribution, what will happen is this p theta will always remain constant, and we know that when it is constant, when it is constant, when we differentiate that thing, it will be 0. Okay, it will be 0. That is why it will not affect it. So that is the thing. MLE and MAP are same when prior is uniform distribution. This can be useful in cases where data is limited or noisy. Where it is useful, MAP is useful in cases where data is limited, where we have limited knowledge, then we need some prior information. Also, if data is noisy, okay, in that case also we can use. Or where there is a need to incorporate domain specific knowledge into the model, means we need to know something before our data. In that case also MAP is used. So this is about MAP and MLE. Suppose we are passing a dice. Yeah, same things you can do for passing a dice also. You have to only change this thing. Okay, whenever you will change this thing, you will get your maximum likelihood estimate. Now for passing a dice also, you will take something as success, like you will take 6 as success, or can take 1 as success. So when you know the success, divided by all your terms, and you will get this. Okay, so this is the difference. Okay, so this is about maximum likelihood estimation and MAP. Okay, maximum a posteriori. Okay, so any doubt in this? What is MAP? What is MLE? Okay, so now we will be moving into a question answer session. Okay, so topic on which the week 5 assignment question are based: artificial neural network and that parameter estimation, that is MLE and MAP. So this is the first question. I request everyone to guess the answer first, and then we will solve the question. Okay, so consider a feed forward neural network that perform regression on a p-dimensional input. So we have p-dimensional input. Let's say this dot p. Okay, this is the p-dimensional input. Okay, the neuron here is p. Input to produce a scalar output. Okay, it has m hidden layers. Now we will have hidden layers, like let's say these are input, this dot neurons. Okay, this dot and dot. Okay, someone is telling C. Okay, we will see these are hidden layers. Okay, this is the input layer, these are hidden layers, and we will have a output layer. Let's say we have only one in output, so let's say, okay, let's erase this, and this is the output layer. So again I am repeating, we have this is the this is the input layer denoted by I. We have p neurons. Okay, this is the hidden layer. We have m hidden layers. Okay, these are m. We have m hidden layers, and each hidden layer has k neurons. Okay, each hidden layer has k neuron. That means k here, k here, k here, and k here. And what is the total? And produces a scalar output. That means only we have one output. Okay, so again I am repeating: input layer, hidden layer, output layer. Input layer we have p neurons, hidden layer we have m hidden layers, and each hidden layer has k neurons. And we have output layer we only have one neuron. Okay, now it has been told, it has been asked what is the total number of trainable parameters in the network. Ignore the bias terms. Okay, So option A pk plus mk square, option B pk plus mk square plus k, option C pk plus m minus 1 k square plus k, option D p square plus m minus 1 pk plus k, and p square plus m minus 1 pk plus k square. Yeah, Bharati is telling C. Okay, any other guesses? Okay, no guesses. Okay, so let me tell you. So total number of trainable parameter, what does this means? Total number of trainable parameter means the connection of all the layers. For instance, this input layer and first hidden layer, if I tell it as h1, so how many connection will be possible? So this p will be connected, this let's say this first neuron will have k connection, second neuron also have k connection, third neuron k connection, and dot 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 p neuron k connection. So we have like k connection, k plus k plus k dot 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 p dot 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 k p times. Okay, p times. Okay, dot 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 p times k plus k plus k dot 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 k times. That means we will have pk connection over here. Okay, from the input layer to the first hidden layer we have pk connection. Now if I say about hidden layer, this hidden layer has k neuron, this hidden layer has k neuron, so k neuron will have be connected to k neuron here. So k plus k plus k times, because here we have input also, here we have k neurons in the second hidden layer also. So again k plus k plus k, k plus k plus k plus dot 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 k, but now this time k times. Okay, k times. So this will be equal to, plus this will be equal to k square. Okay, now k square between first and second. Similarly second and third, again k square, third and fourth again k square. So if we have fourth layer, let's say if we have four layer, so here k square, here second k square, here third k square. That means if we have four layer, then one less layer, we will have total trainable parameters in the hidden layer. That means if we have m layers, then it will be m minus 1 into k square. Okay, now last layer of the hidden layer and output layer. Last layer of the hidden layer and output layer, output we have only one. Okay, so all this k neurons will be connected to this layer. So k only k, right? Only k, nothing else, because all the k neurons will be connected to this neuron. So k, so you will have k connection. So this will be your answer, that is pk plus m minus 1 k square plus k. So this is pk m minus 1 k square plus k. So option C is your correct answer. Okay, option C is your correct answer. So any doubts in this?
M minus 1 k square, can you just repeat?
Yeah, m minus 1 k square. See this hidden layer, let's say we have three hidden layers. Okay, this is this, this is this. Okay, so here we have k neurons, here we have k neurons, here we have k neurons, right? Clear? Now
Yes.
from here to here we will have k square, right? Because k plus k plus k plus k plus k, we will have k times, so k square, right?
Yes, sir.
Similarly, here from here to here also k plus k plus k plus k square. That means k square plus k square, right? K square plus k square. That
Yeah.
means equal to twice of k square. So we have three hidden layers, but we are getting twice of k square. That means 3 minus 1 k square. So that is why we have m layers. That is why m hidden layers. That is why m minus 1 k square. Okay.
So that minus 1, why minus 1?
We have three layers, hidden layers here, right?
Oh, okay.
And we are getting 2k square.
Okay. Got it.
That is why if here m hidden layers are there, m minus 1 k square. Okay.
Got it.
Any other doubt? Okay, no doubt, right? So let's move on to the next question. Consider a neural network layer defined by y equals to relu wx. Okay, relu means rectilinear, uh, relu rectilinear, yeah, this is your relu, that means rectified linear unit, that is relu. So this is your function, right? There it is telling about this type of function, that is rectified linear unit. Okay, so y equals to relu wx. Okay, here x belongs to r of p, that means we have p neurons in our input layer. Okay, and output layer, we have output layer, here we have output layer and input layer only, no hidden layer, right? So here output layer we have output layer will be belonging to rd, that means we have d neurons in the output layer. Output layer. Now w, all the weights, w will be weights, right? This will be connected to this, similarly this will be connected to this, similarly like that. So these are weights in between our input layer and output layer. The relu activation function defined as relu z is maximum 0 z. That means if the input will be minus, it will return 0, because maximum of minus and 0 will be 0. And if your input was positive, it will return the positive number, that is z. Is applied to element wise wx. Find del yi by del wij, where I will be belonging to 1 to d. I will be belonging to 1 to d, that means this is related to the output layer, and j belonging to 1 to p, this will be related to the input layer. In the following option, I condition, yeah, this is a condition. It's an indicator function that returns 1 if the condition is true and 0 if it is false. Okay, so no need to see about this, only this is the condition. Okay, so relu means this thing, yeah, yi max your z 0. Now this z is wx. Okay, this z is wx, z is wx. Okay, wx, that is wij into xj. X is your input, and x is your input because this j belonging from 1 to p. So this xj will be your input and wij will be your weights. Okay, now we will have condition. First condition is if your yi is less than equal to 0. If your yi is less than or equal to 0, then what will happen is this yeah sorry if wij xj will be lesser than equal to 0, then what will happen is this term or your relu function will be equal to 0, because relu, we know, if the input is lesser than 0, it returns 0. Lesser than 0 or 0, it returns 0, and if it is greater than 0, then it will return the same number. So if our first case, if wij xj is lesser than 0, this is case first. Okay, this is case first. This is your first case. First case, if wij xj is lesser than equal to 0, then your yi will be coming 0, because it is maximum of this and 0. So maximum of negative and 0 will be equal to 0. So yi will be coming 0. And when you will differentiate it, del yi by del wix, it will be 0, because yi is 0. So 0 differentiated by anything, it will be equal to 0. So this is our first case. This is our second case. Okay, this is our second case. Second case, if wij xj is greater than 0. In this case, what will happen? In this case, your yi will be this sigma j from 1 to p, because we have this much input. Okay, that is why sigma j from 1 to p, because we have p input, that is why sigma j equals to 1 to p. wij, all your weights into xj. So this will be your yi. Now whenever we will differentiate this with respect to wij, your answer will be xj. So which option is correct? Yi is greater than 0, yi is greater than 0, then xi. No, xi is not correct, xj is correct, right? So option B is your correct answer. Okay, option C, yi, it should be 0, but it is returning xi, so again a false. Yi greater than 0, this will not return, this will not return. So option B is your correct answer. So any doubt in this? Any doubt in this?
Can you please explain this Wijxj?
Wij
The
xj,
second case. The second case.
second case you have doubt. Okay, so second
Yeah.
case, if wij is your weight multiplied by input xj, if it is coming greater than 0. Now greater than 0, what is relu of z is maximum 0 of z, means if I put minus something here, like relu of minus 9, so it will return me 0. Why it will return me 0? Because maximum of 0 and minus 9, that is 0, so it will return 0. So this is your first case. If your wijxj is lesser than equal to 0, it will return yi is 0. And if you will differentiate 0 by anything, that will be equal to 0. So first case is clear. Second case, if it will be greater than 0. If it will be greater than 0, like plus 9. Earlier we have discussed about minus 9. Now if let's say your answer is 9 plus 9. So relu of plus 9. Relu of plus 9 will be equal to maximum 0 and 9. 0 and 9, which is maximum? 9 is maximum, right? So it will return 9. So similarly, when we will do relu of relu, that means maximum wijxj into and 0, and this is greater than 0, then it will return this thing. Okay, when it will return this thing, and when we will do this del yi by del wij, we will get this xj. So option B is your correct answer. Okay.
So one question, that indicator function, right? It's only for yi greater than 0, is it? How will it return that false if it is less than 0?
Can you please repeat?
No, that I condition is an indicator function. That's the question, right? So, is it sufficient to write y greater than 0 only, or is that how that I function is written? Or should we mention the less than 0 also? That's my question.
I condition is an indicator function that returns 1 if the condition is true, or 0 if it is false. Okay.
Okay.
So don't don't take care of this 0 if false or 1 if true. You just focus on this condition. I
Okay.
is taking some condition, okay, and it is returning something. Okay.
Okay.
So this is
So
the thing.
question is about finding dy by dw to be written in that form. Is it?
Quotient, yeah.
Okay.
Quotient, del yi by del wj. Okay. Yeah, quotient is this. Quotient is we have to find del yi by del wij. Okay.
Okay. Okay.
Okay. This is the quotient. Find del yi by del wij. Okay. This is the quotient. Find del yi by del wij. This only you have to focus. Don't focus on this. Only this is condition, that if yi is something, what will be your answer? Okay. If yi is less than something, what will be your answer? Okay.
Okay.
Okay. Now let's move on to the next. Any doubt in this question? Again, an important question. Any doubt? Here we have learnt to use this activation function, that is relu. Okay. Okay. Now consider a two-layer neural network. Okay, two-layer neural network. Y equals to this. Y equals to this. Okay. This sigma stands for your activation function. Okay. So here you have two weights. Okay. It is actually three-layer function. It has been told two-layer because input they have not considered, but actually it is a three-layered function. Okay. You have two weights, one between input and hidden layer, and second between your hidden layer and your output layer. So two type of weights. So that is WA is between wa yeah This okay, someone is joining. Yeah, so what I was yeah, your output will be equal to output will be equal to WB. So earlier this is WB actually, and this is WA. Okay, V is your WA and W is your WB in this question. Okay, so Y equals to this. This is nothing. This sigma is for a transformation function here, and this sigma is for this activation or transformation function here. Okay, so this is the thing. This sigma is for here, and this sigma is for here. So this is the thing, and this is your final output. Let H. Okay, this thing is denoted by H. Okay, so when you are doing this function here, it is denoted by H. Okay, and here it is denoted by here output you will get this is denoted by Y. Denote the hidden layer representation. WA and WB are arbitrary weights. Which of the following statement is true? Note del F with respect to G. Del GF means del F with respect to G denotes gradient of F with respect to G. Now these are the options. Del H, del Y with respect to H depends on WA. Del Y with respect to WA depends on WB. Del H with respect to WA depends on WB. Del Y with respect to WB depends on WA. So any guesses for this? So you all understood the question, right? Anyone who didn't understood the question?
So can you explain it again?
Yeah. So we have considered a two-layered neural network. Actually, two-layer here the input layer is not considered, but actually there is an input layer. So that is why it is called two-layered neural network. So two-layered neural network here it has been given an activation function of the output. Okay, this is the output. Okay, Y equals to sigma this. Okay, so this is the activation function of the output layer, and the activation function of the hidden layer, it is denoted by H, and that is given by sigma WAX. Okay, so this is about denote the hidden layer representation. Okay, now we have two type of weights, right? One, the input to the hidden layer, that is denoted by WA, and second, the weights that is connected hidden layer to output, that is WB. Okay, which of the following statement is true? And this is the notation, that is del FG. That is del F with respect to G. That is del F with respect to del G. So this is the thing. This is the thing. Del GF means del F with respect to del G. So these are your options. So any guesses? Okay, so let me do one by one. So here it has been asked del Y with respect to del H. So this depends on WA. So del Y with respect to del H. This is the Y and this is the H, and in between you have WB. Okay, so I have told you. Okay, some questions is coming. Yeah, so del y with respect to del H, and that will be depends on WA, that is written. This is not minus. I think there is some typing or something mistake. This is not minus. Okay, this is WA, and this is WB. There is no minus here. Okay, this is WB. Okay, no minus here. So first question, it has been asked del y by del H depends on WA.
D answer.
Okay, someone is guessing D. Okay, someone is guessing D. Okay, any other guesses? Okay, no problem. So let us solve one by one. Del y by del H depends on WA. So where is your y? Here is your y, and where is your H? Your H is here. So in between you have WB. So del HY depends on WB, not WA. So this is incorrect. Right? Second option. Second is del Y by del WA. Okay, del y by del WA. Where is del y? Del y is here, and del WA. Del WA is here. Okay, so that depends on WB. Yeah, that will be dependent on WB. So this is right. Now del WA divided by del H with respect to del WA. Where is del H? Del H is somewhere here, and del WA is here. Okay, that will dependent on WB. No, because there in between there is no WB, so del H by del WA we can directly go. So it does not depend on WB. Now last one is del Y with respect to del WB, right? So where is y? This is your y, and where is your WB? This is your this is your WB. So again, del y by del WB, del y by del WB depends on WA. Again, it will not be dependent on WA. So let me check once again here. Del y by del H, 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 del y by del H. Where is del H? This will be dependent on WB, but it is written WA. This is false. Now del y by del WA, del y by del WA, del y by del WA. Definitely it will be dependent on WB as well as del H. Okay, so this is right. Del H by del WA, del H by del WA. In between we don't have WB, in between we don't have WB, so this is also incorrect. And last, del y by del WB, del y by del WB. Now del y by del WB, in between we don't have del WA, so option B is only correct. Okay, B and D is correct. Okay, how D is correct? D is okay. WB are the okay, del y by del WB. Okay, del y by del WB, del y this, and del WB. By del WB depends on WA. How del y by del depends on WA? Del y depends on
While calculating this hidden
yeah,
layer, we will be
yeah,
considering the WA, right?
yeah.
Indirectly, it will
Yeah, yeah,
be
yeah,
depends on
yeah, yeah,
WA.
yeah. Indirectly, it is connected because H is depends on WA. That is why it is given. So option B and D is correct answer. Okay. So D is correct answer. B is correct answer. Okay. A and C are incorrect answer. Okay. Is this clear? Okay, I think it is clear to all of you. Let's move on to the next question. Which of the following statement about initialization of neural network weights are true? Two different initialization of the same network could converge to different minima. Okay, B, for a given initialization, gradient descent will converge to same minima irrespective of learning rate. Option C, the weight should be initialized to a constant value. Option D, the initial value of the weight should be sampled from a probability distribution. So, any guesses? Which are true? Yeah, Bharati is telling B. Initial gradient descent will converge to same minima respective of learning rate. No, B is actually incorrect. Any other guesses? Okay, so yeah, A and D are correct. Okay, two different initialization of the same network could converge to a different minima. So yeah, two different initialization of the same weight. What happens? You see this curve. Yeah, it will be better understood by this curve. You are seeing this curve, right? This is error, and these are weights. Now it has been told that if we initialize different weights, like if we are here, okay, like if we are here, okay, if we are start our calculation here, and if we are doing this if we are doing this error thing. So error, we have to find out the minima, right? We have to find out the minima. So if we are starting from here, we will be stucking over here, and if we are starting from here, we will be stucking over here. So if we will use different weights, we will have different minima. Okay, so this is the thing. Okay, so this is the concept. So option, okay, option 2, different initialization of same network would converge to different minima. So this option is right. For a given initialization, gradient descent will converge to the same minima irrespective of the learning rate. No, learning rate has immense importance. Learning rate we have already seen. Whenever we are updating our weights,
Okay.
whenever we are updating our weights, right, this learning rate has much importance. Okay, so that is why option B is incorrect. That is why option B is incorrect. The weight should be initialized to a constant value. No, constant value we should not initialize our weight, because if we initialize all the weights to the constant value, so what will happen is each neuron will be contributing to the next neuron the same type of feature. So that we don't want. We want different features, different type of feature to the next layer. Okay, so that is why we do not initialize our weights to the constant value. So this is also false. The initial values of the weight should be sampled from probability distribution. That means the initial values of weight should be randomly chosen from a probability distribution. So option D is also right. So A and D are the correct answer. Okay, so option A and D are the correct answer, right? So this is all about question 4. Now we will quickly move on to the question 5th. Consider the following statement about the derivatives of the sigmoid function sigma x. This is your sigmoid function, and tan hx, this is your tan hs function or tan hyperbolic function. Which of this statement is correct? 4 options are given. So first thing is, we have to see what is sigma dash x. So sigma dash x, when we will differentiate it, what will happen when you will differentiate it? It will be 1 by 1 plus e to the power minus x, and yeah, it will be equal to this will be equal to sigma x into 1 minus sigma x. You can differentiate and you will get the answer. Okay, this sigma dash x will be equal to sigma x into 1 minus sigma of x. Okay, so
Option B.
hello. Okay, so when x will be tending to minus infinity, so what will happen is this sigma x will be tending to 0, because here 1 by 1 plus infinity, that is 1 by infinity, that will be 0. So sigma x will be tending to 0, and 1 minus sigma x will be, as sigma x is tending to 0, 1 minus sigma x will be tending to 1. So this is 0 and this is 1. So that means your sigma dash x will tend to 0. So
Option C.
so option B is also correct, right? B is also correct. B is correct. Now your sigma x, when you will see the curve of this activation function, this sigma x, yeah, when you will see this activation function, the range is from 0 to 1, right? The range is from 0 to 1. So as the range is from 0 to 1, where is the question? Yeah, so as the range of this sigma x or this sigmoid function will be from 0 to 1, this sigma x 1 minus sigma x x will be greater than 0. Okay, because this sigma x will be ranging 0 to 1, and 1 minus sigma x, this will be greater than 0. So the maximum of sigma dash x is attained at x equals to 0. So sigma dash 0 will be equal to half 1 minus half, that is 1 by 4. So ultimately what you will have to do, you have to differentiate it, and when you will differentiate it, you will find that the maximum of this sigma dash x will be happening when x will be equal to 0, and whenever you will put the sigma dash 0, you will get this answer, that is 1 by 4. But here it is telling 1 by 8, so this is or this option is wrong. Okay, now we will do the same for this tan hyperbolic function. So tan hyperbolic function, when we will differentiate, we will get this, and here it has been asked for plus of infinity. So plus of infinity, when we will be giving plus of infinity, so tan h of plus of infinity, what will happen? It will be 1. How it will be 1? See, infinity minus e to the power minus of minus infinity, so this will be very small, this will be infinity plus this will be very small, so infinity divided by infinity, that will be 10 to 1. Okay, so this will be 1, and tan of h dash x will be tending to 0, because 1 minus 1 will be tending to 0, so tan h dash x will be equal to 0. So this is actually false, right? This is actually false. Now tan hx, when you will see the curve, you will see the curve hyperbolic function, right? Here you will see the curve, this is your tan hyperbolic function. Here the range is between minus 1 to 1. Okay, the range is between minus 1 to 1. So range is between minus 1 to 1, and then 1 minus when you will put this 1 minus when you will square it, that will be from 0 to 1, right? And 1 minus this, you will be getting 0 to 1. So maximum value of tan h dash x is attained at x equals to 0, that will give the answer as 1. Okay, so this is also correct. So option B is correct and option C is correct. So B and C is your correct answer. Okay, so any doubt? Okay, so let me move to the next question. Statement. Here is a statement and here is a reason, and there are 4 options. So statement: threshold function cannot be used for activation function for hidden layer. Reason: threshold function do not introduce non-linearity. Option A, statement is true, reason is false. Option B, statement is false, reason is true. Option C, both the statement as well as reason is true. And option D, both are true and the reason does not explain the statement. So any guesses? So Bharati is telling A, C, someone is telling A, C, someone is telling C, someone is telling A as well as D. Okay. Okay. So threshold function cannot be used as activation function for hidden layers. So yes, this statement is true. Threshold function cannot be used as activation function for hidden layer. Threshold function, what are the threshold function? That is plus 1, minus 1, 0, 1. Those activation function whose output is 0, 1, minus 1, plus 1, like that are known as threshold function. So here threshold function cannot be used as activation function for the hidden layer. Why? Because first, limited information passing from one layer to next. That means if say if your output of the threshold function is 0, then what will happen? The input that will be taken by the next hidden layer, it will be 0. That means no information is passing to the next layer, which is not
D.
applicable. Okay. Second thing is, all your threshold function are generally non-differentiable. Differentiation is very important because we have seen that differentiation is used to update the weights. Okay, so that is why, as threshold function is non-differentiable and limited information passing from one layer to next, that is why threshold function cannot be used as activation function for hidden layer. So reason is false. Okay, reason is false, but statement is true. That means statement is true and reason is false. So option A is your correct answer. Okay, so any doubt in this? A is the correct answer. Okay, both are true, reason does not explain. No, both are not true. Okay, reason is not true. Threshold function can introduce your non-linear function also. Okay. Okay, How many trainable parameter does a feed-forward neural network contains for a regression on a 3D input to generate a single scalar output? That means you have 3 inputs in your input layer. You have 4 hidden layer, each containing 10 hidden units, each containing 10 neurons. Bias terms are disregarded. So these are your option: A 440, 340, C is 330, and D is 430. So any guesses for this? So we will be using the same formula, that is pk plus m minus 1 k square plus qk. What is p? P is the number of neurons in the input layer. Here you have 3 neurons in the input layer. Okay, 3 neurons in the input layer. Then you have 4 hidden layers, each containing 10 neurons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Similarly, you have 4 hidden layers, each containing 10 neuron. Okay, these are hidden layers. And then you have a output layer, output a single scalar output, only one output. So one output, and yeah, one output. So total number of parameters is denoted by this formula. That is, if we will tell p number of inputs are there, and k number of neurons are there in the first hidden layer, so your connection will be pk, right? Similarly, your connection between hidden layer and hidden layer will be equal to k square, and that will be one layer less. Okay, because one layer less. So that is why m minus 1 k square. And lastly, if you have q number of output, then q into your q into neurons in the last hidden layer. So that is why qk. So that is your formula. But here, what is the value of p here? P, we have 3 inputs, so value of p is 3. K, we have 10 inputs in the hidden layer, that is why k is 10. So p is 3. Let me write here, p is 3, k is 10, and q is 1. Okay, and m is number of hidden layer. Number of hidden layer are 4, right? So your answer will be 3 into 10 plus 4 minus 1 into 10 square plus 1 into 10. So that will be 340. So 340 will be your answer. So option B is your correct answer. Okay,
Sir, please can you please repeat that PKQM values, sir? 3, 10, 1, 4. P is also number of neurons in the same input layer. K is also number of neurons in the input layer. Both statements are same now, sir. P and K.
Oh, sorry, hidden layer. Here actually it should be hidden layer. Okay, I think it should be hidden layer. Okay, not input.
Can
Input
sir,
hidden, and then output layer.
can you tell me the values of this, sir? 3, 10, 1, 4
See,
repeats.
how many trainable parameter does a feed-forward neural network contain for a regression on a 3D input? 3D input. Okay, 3D input. That means in input layer you have 3 neurons. That means the value of P will be equal to 3. Okay, up to this it is clear?
Yes, sir.
Okay, now to generate a single scalar output. That means in the output you will have 1 neuron. Single
Yes.
scalar output. Okay, so P is clear, Q is clear. Now 4 hidden layer, that means M is the number of hidden layer, that is why 4. Okay,
Okay.
and each consisting 10 hidden units, that means each hidden layer consists 10 neurons, that is why K equals to 10. Okay, clear, right?
Correct.
So that is why Pk plus M minus 1 K square plus Qk, you put the value, you will get 340. Okay, so option B is your correct answer. Okay, clear, right?
Yes,
Okay.
sir.
Okay, let me move on to the next question. If the step size in a gradient descent is too large, what can happen? Option A, overfitting. Option B, the model will not converge. Option C, we can
Spread
reach
ingredient you can reach
maxima
to
instead of minima.
love
Option B, none of the
too
above.
low.
So,
Maxima instead of minimum.
so the thing is, if the step size is your learning rate. If your learning rate is very much large, so what it will do it, your last step, it may oscillate around the minimum or
Answer
even
C.
diverge. Yeah, we can reach maxima instead of minimum. No,
Answer C.
no, maxima instead of minima, we will reach minima. We can reach maxima also, but option C we cannot tell. Okay, we can only say that model will not
Option B.
converge. That means it will not reach the local minimum. Okay, so that is the right answer. So option B is your right answer. Overfitting is always related to data. Okay, more than model, overfitting is related to data, but here it is related to model. Okay, eta is your model parameter, so that is why overfitting we cannot tell. Okay, we can reach maxima instead of minima. Again, this thing we cannot tell, maybe, may not be, we cannot tell, but the model will definitely not converge because our step size is very much large, so we will keep on oscillating. Instead of finding the local minima like this, instead of finding local minima from there, if we search here, because okay, from here, first we are searching here, right? And then if our step size is very much large, then we will search here, so we are missing the minimum. Similarly, from here, now our next step size is here, then again we are missing the local minima, or we are missing the minima. Okay, so that is why our model will not converge if our gradient size or step size is much large. So option B is our right answer, right? So option B is our right answer. So now move on to the next question. The last layer of ANN is linear for dash and softmax for dash. So option A is regression. Option B classification. Option C regression classification. Option D classification regression. So any guesses? Linear for what and softmax for what? Yes, Sandeep is telling B, right? Classification. No, linear is for regression and softmax is for classification. So again I am telling linear is for regression. Linear, whenever we are talking about linear, then it is for regression. Okay, linear, we are using linear function for regression. We are using softmax or sigmoid function for classification. Okay, classification, how we are using, we are taking some threshold. Below the threshold we are taking as one class, above the threshold we are taking as another class. So that is why sigmoid or softmax. What is ANN? ANN is artificial neural network. Okay, it can also be told as NN, that is neural network or neural net. We generally use ANN, that is artificial neural network. So the last layer of artificial neural network, linear for regression and softmax for classification. So option C is our correct answer. Okay. Okay. Again, this is also a simple question. Now, some disturbance is there. Okay. Which among the following statement is true? MAP estimates suffer more from overfitting than maximum likelihood estimate. MAP estimates are equivalent to ML estimates when prior used in the MAP is uniform prior over the parameter space. Option C both A and B, and option D none of the above. So any guesses for this question? Yeah, someone is telling C. C is telling, but is the C is the correct answer or B is the correct answer? Okay, B, someone is telling B. So C. MLE aims to find parameter value that maximize the likelihood of the observed data. Whenever we are talking about MLE, we are solely relying on data, which can lead to overfitting. See, data is the thing that leads to overfitting rather than model. Okay, so data is the thing that always leads to overfitting. If our data is sparse or noisy, so what will happen? MLE will be more overfitted. But if we talk about MAP, as we have some prior knowledge about the model, The prior can be thought as incorporating additional knowledge or regularization in the estimation process. So we have some prior knowledge. So as we have some prior knowledge, so it will not overfit the model. So MLE is more likely to overfit than MAP. So the reverse statement is true, not this statement. That is, MLE is more likely to overfit than MAP. Now talking about the uniform prior I have already told, if your prior is uniform, then your MAP will be equal to MLE according to your Bayesian learning. So option B is your correct answer. Option A is not correct, option B is correct, so option B is your correct answer. Okay, so is this clear? Clear, right? Okay, so by this I am ending the session for today. Okay. So we will meet on the next Monday. Kindly practice all this, and this slide will be provided to you all in that problem solving session. You will get a Google sheet, and that Google sheet you will have with my name, Ayan Paul. You will have the week 5 slides, week 5 this YouTube video. This is recorded, so this will be provided to you all, as well as there will be a folder. In that folder you will get this slide. Okay. Okay, so by this I am ending the session for today. Bye. Okay.